Welcome to iLectureOnline, and here's our second look at the second law of thermodynamics. The previous video was our first look, here's our second look, and here we're dealing with the concept of heat flow. And as we already discussed, we understand that heat flows from a hot reservoir to a cold reservoir, and that's what nature does, that's what the universe does. Everywhere in the universe where you look, and it seems like that is one of the major purposes of the universe, is to have heat flow from hot to cold places, and we never see it the other way around. And there's a reason for that. The second law of thermodynamics prohibits that from happening. So what we can see is that if we have a heat engine, the only reason why it can work, why we can actually get work out of a heat engine, because the natural process allows heat to flow from a hot reservoir to a cold reservoir. Matter of fact, we don't need to do anything for that to happen. It just happens automatically. Whenever there's two things that are at different temperatures, heat will be flowing from the hot to the cold. That can be guaranteed. It always happens all the time, 100% of the time. So once the heat flow has completed and heat has flown from hot to cold, and we extracted some of that heat flow and converted to work, once it reaches the cold reservoir, we're not able to get it to go the other direction. It always goes from hot to cold, never from cold to hot. Matter of fact, for that to happen, for the heat to go in the other direction, we would need something like this. And what we've learned is, to do that, we actually need to put work into it. It doesn't happen on its own. It requires an input of work. Matter of fact, this is a diagram of a refrigerator. And what a refrigerator does, it grabs heat out of the cold reservoir, the inside of the refrigerator, which is already cold, takes heat out of it, dumps it into the kitchen, where it's warmer, thus making the inside of the refrigerator even colder. And then, of course, at the same time, heat seems to seep through the insulation from the outside back to the inside, and you have this constant flow, the natural flow from hot to cold, and then the performance of the compressor of the refrigerator to force the heat in the cold air to go back to the outside, making it even colder inside. This requires work. If we could get this to happen without the input of work, which would be this picture right here, you can see that no heat is required. The second law of thermodynamics says this is simply not possible. Because if you look at the coefficient of performance of the refrigerator, and we'll look at that concept a little later, but the coefficient of performance is defined as to the amount of heat you can grab out of the cold reservoir and expel it to the kitchen, to the hot reservoir, divided by the work, is how efficiently, a way you could look at it, but they like to think of it in terms of the coefficient of performance, how much performance the refrigerator has. And of course, you want to maximize the heat being taken out of the refrigerator and minimize the amount of work you want to do. And so you want W to be small, Q sub C to be large, and so you want the ratio to be as large as possible. In the limit, W would go to 0, and the coefficient of performance would go to infinity. And what they're saying is that K must equal infinity for that to happen, and that simply is not possible. So to write it in the English language, you can say it is impossible for heat to flow from cold to hot. And that is another way of looking at the second law of thermodynamics. Not quite straight, but you get the picture.